Today, we're diving into something pretty mind-blowing in the world of robotics. We're going to break down how researchers are finally getting robots to do those super delicate, complex things that, only humans could do before. Think making a cup of tea or even folding paper. So how on earth did they crack that code? Well, let's get into it. I mean, really think about this for a second. You can ask an AI to rate you a Shakespearean sonnet and it'll spit one out. But ask a state-of-the-art robot to just make you a simple cup of tea. Suddenly, it's a whole different ballgame. It gets really complicated, really fast. So why is something that feels totally automatic to us one of the absolute biggest hurdles for robots? That's the huge problem we're going to unpack today. All right, so this all comes down to what you might call the clumsy robot problem. The old ways of teaching these machines just aren't cutting it. For years, we've been trying to give robots these fine motor skills, but the methods we've been using, they've got some pretty major drawbacks. So let's look at the two main old-school approaches. First, you've got teleoperation systems. This is basically where a person controls the robot directly, kind of like a high-tech puppet. And sure, it works, but man, is it expensive and clunky. You can't just take it anywhere. Then there's the other way, vision-based motion capture. This uses a bunch of cameras to track movement. The huge problem here, though, if your hand or an object blocks the camera's view, even for a split second, the whole thing can just fall apart. Not very reliable. This brings us to a portable new solution, DexCap. See, the researchers were thinking, okay, what if we could build something that's super accurate, but also portable, something we could use to grab data anywhere, out in the real world? And that's exactly what led them to the hero of our story today, a system they've named DexCap. So what exactly is DexCap? Well, at its heart, it's a totally new way to record all the data from a person doing a really complex hands-on task. And the two most important words here are scalable and portable. This is not some giant, expensive setup stuck in a lab. No, this thing is designed to go out and be used in the real world. And the setup is beautifully simple. That's the key. A person just wears a camera on their chest, which captures their first-person point of view. Then they put on a pair of these really cool motion capture gloves that track every tiny movement of their fingers. And finally, there's a tracker on their wrist to know where their hand is in space. Put it all together, and you get this incredibly complete picture of the action. And since it's also lightweight, you can literally use it anywhere. And this is the really critical part. Someone can just put on the DexCap gear and go about a task, say making tea, just like they normally would. The system is capturing everything, the super precise 3D movements of their hands, plus what's called a point cloud of the environment. Just think of that as a digital 3D map made of millions of tiny dots. But here's the absolute game changer. The robot doesn't even have to be there for any of this. It's all about capturing the human skill first. All right, next up, teaching the robot hand. This is a 3-phase process for translating human motion. So we've got all this amazing, rich data from the human. Now comes the magic trip, right? How do you take all that and actually teach a robot to do the same thing? Well, it turns out there's a really clever 3-step process for it. Okay, so here's the training pipeline. First up is action retargeting. This is where the system matches the human's finger positions to the robot's hand. It uses a cool trick called inverse kinematics, which is kind of like if you just told your arm, put my hand on the doorknob, and your elbow and shoulder just automatically figured out how to bend to make it happen. Step 2 is visual retargeting. This basically transforms that 3D point cloud we talked about so the robot sees the world from the exact same perspective as the human did. It's putting the robot in the human's shoes visually. And finally, you have policy learning. This is where the AI takes all that information and learns from it, creating what's called a policy, which is just a fancy word for a playbook. It's the robot's set of rules for what to do in any given situation. Now get this. This is the part that is just absolutely wild. The robot can learn a whole complex skill from just 1 hour of human data. Seriously, 1 hour. That is a monumental leap forward in efficiency. It means you can completely skip all that tedious, super expensive direct robot puppeteering. So, that brings us to the tea-making test. Can the new policy handle a more complex, real-world task? The robot has its initial training, and it's already doing pretty cool stuff, like handling objects it's never seen. But the researchers wanted to see what it was really made of. They decided to throw a real curveball at it, a much, much harder challenge, making a full cup of tea from start to finish. We're talking multiple steps, really precise movements, a true test. And at first, it didn't go perfectly. The initial programming, the policy, had a few weak spots. For example, sometimes the robot's hand just wouldn't quite reach the right position. And it really struggled with those tricky two-handed tasks. Like holding a jar steady with one hand while trying to twist the lid off with the other. It just couldn't coordinate. So this leads to the next huge question, right? When the robot messes up, what do? Do you have to just scrap everything and start from scratch? Go out and collect another full hour of data? I mean, that would kind of defeat the whole purpose of being efficient. There has to be a better way, a way to fix the mistakes without all that effort. And that's where they came up with this brilliant idea, adding a human in the loop. It's a super clever way to do rapid corrections. The answer wasn't to take the human out, but to bring them back in, just in a much, much smarter way. So this correction system has two different modes. The best way to think about it is like a driving instructor with a student driver. For small mistakes, like drifting a little bit in the lane, the instructor can use residual correction. The human operator, wearing the same DexCap gear, just makes tiny adjustments, a little nudge here, a small correction there, to what the robot is already doing. But if the robot is about to make a huge mistake, like run a red light, the instructor can grab the wheel. That's teleoperation mode, where the human takes full, direct control to show the robot exactly what it should have done. And here is another mind-blowing number. You don't need hundreds or thousands of these corrections. The robot's policy can be fine-tuned and massively improved with as few as 30 human interventions. Just 30. They just take that tiny little data set of corrections, add it to the original hour of data, and retrain the whole thing. It is just unbelievably efficient. So, what's the result after all this fine-tuning? Well, this is where we see the whole system truly shine. This is dexterity unlocked. The payoff is huge. Check out this number. With that small handful of corrections, the success rate for the task jumped by more than 30%. I mean, that's not just a small tweak. That is a massive improvement that takes the robot from, uh-oh, it's probably going to mess up, to, wow, it's actually getting it right consistently. And this really gets to the heart of why this whole system works so well. When you build a robot's brain on this rich 3D data collected in the wild, it just blows the old methods out of the water. Those traditional approaches that just used flat 2D images, they can't even come close. It really shows you that the quality of the data you start with makes all the difference in the world. So, the end result? The robot can now nail that really tricky tea-making task every single step, from start to finish. But what's even cooler is that it's not just a one-trick pony. This same exact framework can be used to teach it other incredibly precise skills. Things like how to use a pair of scissors to cut a piece of paper. Skills that used to be pure science fiction for a robot. And all of this leaves us with a pretty epic question to think about. For the very first time, we actually have a method that's portable, that's efficient, and that scales for teaching our most human physical skills to a machine. This could change everything, from how we build things in factories to how we perform surgery. The door has been blown wide open, so the only question left is, what do we teach them next?